So in the previous lectures, we were discussing about differential pairs, how to characterize differential pairs from small signal point of view, but also we discussed qualitatively how does a differential pair behave for large signal inputs. So in this lecture, I'll very quickly take you through some very standard differential pair architectures, and also we will later discuss one of the a very important differential amplifier circuit called a differential to single-ended transistor, differential to single-ended converter. So first, what I've shown here is a simple differential pair with a resistive load. In practice, especially in integrated circuits, differential pairs used in integrated circuits, we do tend to have different kinds of loads. We don't restrict ourselves to just resistive loads. So I'm just going to show some very commonly used loads in differential pair circuits. The first one shown here is what we call a diode connected load. Since it's a diode connected load, can you quickly say what will be the voltage gain of the circuit, differential voltage gain of the circuit? So let GMP be the transconductance of PMOS, GMN be the transconductance of NMOS. So then what will be the differential voltage gain? See, differentially this node comes to AC ground, so directly you can do a half circuit analysis. So it will be GMN upon GMP. So what is the advantage of this amplifier? Does the gain of this amplifier depend upon the bias current? Does it depend on bias current? No, right? So what does it depend upon? It depends upon the ratio of, you can substitute beta n by beta p. So it depends upon beta n upon beta p. So beta n is mu n Cox W by L. So you get mu n W by L Nmos by mu n W by L PMOS. So we get ratio of, mu p. So we get a ratio of mobilities and W by L ratios here. Okay, so it definitely helps you in getting a constant gain. Now what about this circuit? If you are to find, again, this is also a diode connected load. Both these circuits are diode connected load circuits. What will be the voltage gain of this circuit? So this again, you can see it as an AC ground. If this node comes to AC ground, what will be the voltage gain of this circuit? Now let's assume GMN by, let me call, this is load GML and this is the input transistor GMN. So in that case it will be, so can I say it's going to be GMN upon GML? Okay, I've ignored R0 here. So I'm assuming you'll know how to include R0 in the analysis. Yeah. So it will be GMN by GML. So what will that be? That ratio be? If you are to ask to find this ratio GMN by GML, so can I say it will simply be the W by L ratio of the input NMOS transistor by the W by L ratio of the load transistor. So there is not even a mobility dependence here. The gain is just dependent upon the ratio of widths. If I assume the length to be same for both the devices, then the gain will simply be the ratio of the widths of both the MOSFETs. Okay, so that's one additional advantage of this circuit. So the gain, we said, is independent of the bias current. So even if the bias current changes a bit in both these circuits, your gains will remain more or less constant. Now the third one, which is the more commonly used differential pair for very high voltage gain. If you want to get the whole idea of using differential pairs, of course, they should give you all the benefits of a single-ended amplifier, which is high gain and all of the high input impedance and all of that. At the same time, they should be able to reject common mode variation. So that is the reason why we go for differential pairs. Now what I've shown here, this is input is your standard conventional NMOS input pair. And these two are what we call current source loads. Okay, these two are the current source loads. So generally, we discussed how to realize current sources. We realize current sources using MOSFETs itself. So this is a current mirror, and these two transistors mirror the same current. So they mirror I by 2, I by 2. So I've written the same W bells for all the three MOSFETs. So they are going to mirror the same current I by 2 into both these arms. Okay, so this is, if I draw a single-ended equivalent, this will probably look something like this. So this will be a single-ended equivalent. So this is some fixed at some bias voltage. So this will be your single-ended equivalent for this differential circuit. What will be the voltage gain of the circuit? If I again, this is the axis of symmetry, what is the voltage gain? So let's assume this is Nmos and PMOS, GMN, RON, GMP, ROP will be there, transconductances and output resistances. So what will be the gain in terms of GMN, RON and ROP? See, the input transconductance, so when you do the shorts, I mean, when you do a half circuit analysis, you should instantly be able to see that this circuit, this node will come to AC ground, the circuit will reduce to something like this. So the circuit, the half circuit will just look like this. I mean, so you'll have the input pair and the load transistor. Now this node, what will be this voltage? What will be the node voltage at this point, small signal wise? So you're pushing a constant current through this device, so which means its bias current cannot change. If its bias current cannot change, this is at AC ground, so this also has to be at AC ground. Okay, so since that is AC ground, so this node will come to AC ground. So now you have applied your input at this point. So what is the voltage gain of this amplifier? This is a common source amplifier. So what is the voltage gain? So this is Nmos, this is PMOS. So the transconductance is GMN of this device times output resistance. Looking up, it is ROP. Looking down, it is RON. So it's ROP parallel RON. That's the voltage gain of this differential voltage gain of this circuit. Okay, so far we have seen three different ways of building a differential pair with the different loads. Input pair is always NMOS in all the three amplifiers. The input pair was always an NMOS input pair, but the loads I kept changing. We began with the first load we discussed was a resistive load. So this is a pure resistive load. You connect two resistors, you get the pure resistive load. Now these two are, for small signal point of view, these two can also be seen as resistive loads, but they are nonlinear resistors. So as you may be aware by now, that if you short circuit gate and drain of a MOS device, then this will emulate a behavior of a resistance. But this resistance is a nonlinear resistance. Unlike the linear resistor, for a linear resistor, the current passing through the device is just a function of, it's independent of, it's just a function of the voltage across it, it's V by R. Okay, it's linearly dependent on the voltage. Whereas for this device, for a two-terminal MOS device connected as a diode, the IV characteristics will look something like this. So this is a nonlinear characteristic. So therefore, I should say that this will behave like a nonlinear resistor. It's a resistor, but it's a nonlinear resistor. So these two loads are what we call the diode connected loads. So this is an PMOS diode connected, and here we have an NMOS diode connected load. Okay, and the third one, this is what we call as the current source load. So we have a current source and we replace the current source with a PMOS device. Okay, so one of the questions that's being asked is, what if I'm assuming that these two currents are I by 2, I by 2. See, on the lower half, each transistor is trying to carry a current I by 2 and I by 2. What if the upper half currents don't match? Yes, that's a serious problem with the circuit. We will discuss this in the next, probably not in this course. So there are some circuits to ensure that that doesn't happen. So those circuits are called common mode feedback circuits. See, what will happen is, if the upper current is not equal to the lower current, the lower half is consuming a current I by 2. And if the upper half is not exactly equal to I by 2, some I by 2 plus delta I, then this node voltage will keep increasing because you have a very high impedance at this node, and any excess current flowing through that will create a huge voltage drop. So that's the problem, but this needs to be fixed. That can be very clearly addressed using some separate set of circuits. So those are the biasing circuits called common mode feedback circuits. We won't discuss it now. Right now you can just take that this voltage has come to some steady state value, DC value, the output of this transistor. So this load is what we call a current source load. Okay, and this gives you the highest gain among all the MOS based loads. So if you take all the MOS based loads, this will give you the highest voltage gain. The gain is given by GM into ROP parallel RON. The next one, so far when we showed the transistor here, I mean the current source here, we were always showing it as an ideal current source. But we discussed in the last lecture that even that current source is realized using a current mirror that in this way as shown here. So we'll take a current, mirror it maybe 1:1. So then this will behave as a current source of value I. So what is the output resistance of this current source? Let this transistor be T. So T is this transistor. So what will be the output resistance of this current source? Small signal output resistance, ROT, right? It's going to be small R naught T. So this is going to be ROT. So this transistor is what we call the tail transistor. So this node, this current source is called the tail current source. And this transistor is your tail transistor. Okay. So this is a tail current source and this is realized using a tail transistor. Okay. Now, so for example, in this circuit, if I ask you to find out what is the differential gain, assume that this tail transistor has a finite output resistance ROT. What is the differential gain of this circuit? Differential voltage gain. Differential gain. So I'm not asking common mode gain, I'm asking you differential gain. Differential gain, this node will come to AC ground. For differentially, it doesn't matter whether you have a resistor or not. This lies along the axis of symmetry, so that node will come to AC ground. Because it comes to AC ground, so then it will be GM times R naught N, the R naught of this in parallel with R, the upper resistor here. If you ignore R naught, it will be GM times R itself. It will be just approximately equal to GM times R itself. So differential gain remains the same. Even if this current source has a finite resistance, differential gain is unaffected. So that doesn't change. Right? So even because this resistance falls on along the axis of symmetry, so it really doesn't matter. But what about common mode gain for the circuit? ACM, what will that be? For ACM, remember you'll have to draw ACM, you'll have to draw the common mode half circuit. So this I can replace it by a resistance of value ROT. So again, I can split this into two resistors of value, 2 ROT in parallel with 2 ROT. So what will be your, and I can open circuit this node. So what will be your common mode gain now for this circuit? ACM will be GMR, approximately this will be GMR upon 1 plus 2 GM ROT. I'm ignoring R naught of this MOSFET, which is fine. So this is an approximation we are making. Okay, yeah. So this is what you get for the circuit in the presence of a finite tail current resistor, the tail current output resistance. Now the next one, we will slowly extend. So far what we have seen, all these amplifiers are common source amplifiers, right? All these amplifiers are common source amplifiers. And we have seen the different ways of realizing voltage gain using a differential common source amplifier. So one of you are asking, ROT is the output? Yes, exactly. So ROT is the output resistance of your tail transistor. So we had this current source, tail transistor. So this is V bias. V bias is generated using this diode connector device. So this transistor's output resistance is ROT, the resistance looking into the drain of this transistor. Yeah. So ACM is given, so we have so far discussed common source amplifier configurations. Now, I've also introduced what happens when in practice you will have a tail current source whose output resistance will determine what your common mode gain is. Okay. So now, The next one, naturally, how do you build a differential telescopic cascode amplifier? So telescopic cascode, we said, if you want to get useful gain out of a cascode amplifier, the load has to be a cascode load. Otherwise, we are not going to get a good gain out of a cascode amplifier. The load has to be a cascode load. So what I've shown here is a cascode amplifier with a cascode load. So to draw the differential version, I can start with this. So what I've shown here, this is one half of the circuit. Take an identical half and connect the two transistors, the source couple, connect the two sources of the input pairs, and you can just connect a current source here. You have a current biased differential cascode amplifier. Okay, of course, I can generate these bias voltages using a current mirror. This is a very poor implementation of the current mirror, but you can even use a wide swing current mirror if you want to. Yeah. So this is how we realize a cascode amplifier, a fully differential Nmos input telescopic cascode amplifier. Okay. So what will be the voltage gain of this? So let's assume this device is 1, 2, 3, 4. Okay, 1, 2, 3, 4. So these are the number of devices. So can you tell me what will be the voltage gain of this fully differential cascode amplifier? Again, axis of symmetry, this node will come to AC ground. So it's as good as analyzing a single-ended cascode amplifier. What will be the voltage gain? So we have a single-ended cascode amplifier. So this is one. See, the GMs are very important. So when you write an expression for the voltage gain, so first find out what is the short circuit transconductance. Okay, yeah. What is the short circuit transconductance? This is 1, 2, 3, and 4. If I'm finding out the short circuit transconductance, what will that be? What's GM or capital G? What is the short circuit transconductance in the circuit? GM1, right? It will depend on the GM of this transistor. So GM1 is the short circuit transconductance. That multiplied by output resistance. The output resistance is the resistance looking up. The resistance looking up will be R0 of this device, so which will be RO4 times GM3 RO3. RO4 times GM3 RO3 of this device. That in parallel with the resistance looking down, which is going to be RO1 times GM2 RO2. So your total gain is going to be GM1 times GM2 RO2 RO1 in parallel with GM3 RO3 RO4. This is your expression of gain for a cascode, for telescopic cascode, a fully differential telescopic cascode amplifier. Okay, so similarly, you can also find if your current source was now realized using an Nmos device in saturation region. So this is some V bias. I can generate it using a diode connected transistor. Okay, so one of your questions is, why are we not considering the tail MOSFET's output resistance? See, we are calculating the differential gain. When we are calculating the differential gain, all the nodes along the axis of symmetry will come to AC ground. So this node will also come to AC ground. So that's why this tail resistance doesn't matter. Even if you have a tail transistor, the resistance will not play any role when you are finding the differential gain of the circuit, which is why we don't consider it. But when we consider common mode, we have to consider the tail transistor's resistance as well. Okay, how do we decide the bias voltages? We'll come to that. So probably not in this semester's course. We'll spend extensively on the analysis and design of CMOS op-amps the next semester's course. So at that time, we will go in much greater detail how to generate all these bias voltages. Okay, so we should design those bias voltages such that we maximize the voltage swing at the output. So that should be the goal, and we'll talk about that in much greater detail in the next semester's course. So this semester I'm just introducing you to the circuit, and you should know how to analyze it. Yeah. Okay. So the next one is the other more Yes, so you're asking, don't we have current source biasing in the circuit? I saw a voltage source later. No, this is current source biasing. What I've shown here, this is a current source biased differential pair. So this is nothing but a current source here. Okay. So we will now discuss what we call, yeah. So we will now discuss single-ended to differential and differential to single-ended converters. So generally, the whole idea of introducing or making a signal differential is that we will be able to reject common mode noise. So we said that's one of the reasons why we convert differential single-ended signals to differential signals. So in the beginning of the lectures on differential amplifiers, we began with our discussion on how to convert a single-ended signal to a differential signal. One circuit we discussed in the beginning, we said, was a center tap transformer. If you take a center tap transformer with 1:1 turn ratio, and then the center of the secondary of your transformer is grounded, then the voltage between these 2 points will be differential. With respect to this common ground, you have now generated a differential voltage. So we have two signals which are exactly 180 degrees out of phase. Okay, so this is, we saw how to convert a single-ended signal to a differential signal. The second approach we said we discussed using MOSFETs. Can we convert a differential single-ended signal to a differential signal? We said let's take an input signal Vi and use a voltage divider or generate Vi by 2 out of it. Divide it by 2, then apply it to a circuit shown here. So first apply Vi by 2 to this transistor here, to the common drain. This is a common drain amplifier. And this one is a common source amplifier. Apply Vi by 2 to both these amplifiers, and let's look at the outputs of both these transistors, of both these circuits. What is the output at this point? Small signal. So let's first look at the small signal output. This is what a common drain configuration. So we have a common drain configuration. Let's ignore R0 for the time being. Let's assume R0 is infinity. If R0 is infinity, what will be the output at this point? Right, if R0 is infinity, this resistor is open, this transistor is, the node, the impedance looking down is infinity. So therefore it's a common drain configuration. If the drain current cannot change, so source voltage should follow the gate voltage. So this is Vi by 2. Now the next circuit, what I've shown here, this one is a common source amplifier. So we'll analyze the next half of the circuit. This is a common source amplifier, and I'm choosing identical devices. Both these devices are identical. So this is a AC ground, drain is also AC ground, and you're supposed to find the voltage at this point. What will be the voltage at this point? The looking up, the resistance is 1 by Gm N. Looking down, the resistance is infinity. So the output resistance is 1 by Gm, transconductance is Gm of this device. So V0 will be minus Vi by 2. So what I've generated here is Vi by 2 and minus Vi by 2. So I've generated two voltages which are differential in nature. Now, what will be the DC levels for these two amplifiers? What will be the DC levels at these two nodes? What is the DC level at this node and DC level at this node? Is that Vx or something else? See, Vx is the gate voltage at this point. Let's assume this MOSFET, I have biased them in such a way, each of them is carrying some bias current I with some overdrive voltage VOV. Both of them are carrying this with an overdrive voltage of VOV. So what will be this node voltage? Output now. See, you have this node voltage DC is Vx. So this node voltage VOCM, I'm going to call it V out common mode. Can I say that will simply be Vx, the gate voltage here, minus VGS of this MOSFET. So that will be Vx minus VOV minus VTN. That's it. And that's the same DC voltage for both the nodes. For both these nodes, the DC voltage is exactly the same. Okay, but the sinusoid, the AC signals riding on top of them will be 180 degrees out of phase. So now I have generated a differential signal starting from a single-ended signal. Started with a single-ended signal, I have now generated a differential signal. So this is S to D, single-ended to differential converter. Okay, so both the inputs should see same common mode inputs. When you are converting single-ended to differential, you should see the same common mode DC levels, and any common mode noise source should also see same transfer function to both the outputs. For example, if there is some noise on the supply, it will see same paths to both the outputs. Similarly, noise on the ground, that will also see same paths to both the outputs. Okay, so that's the condition that you'll have to keep in mind. So this circuit is a single-ended to differential converter. Yeah, why is the DC level not equal to VDD minus V over drive? See, you should always understand that V over drive is your first. I think the question comes here because this way, so the drain voltage is at VDD, and you are assuming the drain to source voltage of this to be equal to VOV. Then yes, maybe we can say the source voltage is VDD minus VOV. But the point is, this is a MOS device in saturation. You don't know what the drain to source voltage is. So usually the drain to source voltage will be set by the circuit to which it is connected to. Okay, to the circuit to which it is connected to. So that's why you can't use VO. We don't know what the drain to source voltage is. Minimum drain to source voltage can be VOV, that's it. But we don't know the exact value, so we can't write that. See, the gate voltage is at Vx. The gate to source voltage, I'm calling it as VGS. So the output voltage V0 will be equal to Vx minus VGS, the VGS of this device. Once you fix your bias current at DCS, this is fixed. VGS is fixed. Okay, then you get this. Yes, so I'm assuming that this input voltage Vi, I'm dividing it by half initially. Okay, I'm dividing it by half. See, even if you don't divide it by half, you are going to get what? VCM plus Vi and VCM minus Vi. That's it. You're going to get VCM plus Vi and minus Vi. And it's still differential. It's not, it's still differential. We'll now analyze another circuit. So why don't you analyze this circuit and tell me what will be the output voltage for this circuit? The VO minus, I'm calling this VO minus and VO plus. What will be VO minus and VO plus for this circuit? See here, this is not a fully differential circuit because one end is at AC ground. I mean, I've connected it to ground, so which means there is some common mode voltage I've applied here. So AC wise, it is at ground. What will be the output voltages for this circuit? So ignore R0, assume R0 is infinity. So and quickly analyze and try to find what will be V0 and VO minus. So this current source is ideal. So go step by step. So let's find out what is the source node voltage first. What is the source node voltage? To find out what is the source node voltage, see, keep in mind, what is this? See, the sum of the two currents here, small signal currents. What will be the value of the sum of the two small signal currents if I call this I1 and I2? 0, right? Because the sum cannot change. So which means it's intuitive that I1 should be equal to minus I2. So if I have some small signal current flowing in this direction, the exact same small signal current has to flow in this direction. So if I'm going to call this as GMN and GM as the transconductance of both these devices, find out what will be the small signal current. So for that, you need to know what is this small signal voltage Vx. What do you think will that voltage be? What will be that node AC voltage be? So to find the AC voltage, you can try, what is the looking in impedance here? I'm looking into the source of this transistor. What is the looking in impedance? I'm asking small signal voltage. So what is the looking in impedance? You're looking into the source, 1 by GM. So I'll draw the circuit here, small signal wise. This current source is open. I have a resistance of value 1 by GM looking into this node. Similarly, the drain resistance of this transistor looking up, the drain resistance is 1 by Gm again, because right, that's a Nmos. So now, can you tell me what will be the source node voltage? Assume R0 is infinity here, so this is Vx. What will be the source node voltage? So I'll redraw this, so I can draw this resistance as 1 by Gm here. So what will be your output node voltage? So it's a common drain amplifier, right? So you see, this is a common drain amplifier with 1 by Gm as a load. So what will be the voltage gain? The voltage gain, can I say it will be GMRL by 1 plus GMRL? So if you're going to connect 1 by Gm, so it will be half. So this will be Vi by 2. And what is the drain node voltage? What is the drain node voltage? It's a common source amplifier with source degeneration. When you're looking into the drain, it is common source amplifier with source degeneration. So it will be Gm by 1 plus Gm RL, I mean Rs. Rs here is 1 by Gm times 1 by Gm. So it will be 1 half with a minus sign, of course. So this V0 minus is going to be minus Vi by 2. So that's your minus Vi by 2. Now, we know this node voltage, which is Vx. This node voltage is Vi by 2. So this will be a common gate amplifier. So what will be Vo plus? R0 is infinity. If R0 is infinity, gate voltage is at Vi by 2. And it's a common gate amplifier with a load resistance of, so I'm just redrawing the circuit here. So this is a common gate amplifier with a drain resistance of value 1 by Gm. And we have applied Vi by 2 here. So what will be the voltage gain here? Vo plus. So if I apply Vi by 2, you can visualize the current Gm Vi by 2 flowing through this. Gm Vi by 2 flowing through this. So it will be Vi plus Vi by 2, right? Gm Vi by 2 flowing into 1 by Gm. It is plus Vi by 2. So we have plus Vi by 2 here. Okay. So this is also a differential to single-ended to differential converter. So this circuit took a single-ended input Vi and generated two voltages, Vi by 2, minus Vi by 2 and plus Vi by 2 from small signal point of view. Of course, the derivations we made some assumptions R0 is infinity and all of that. If you include R0, it will not be perfectly differential, but still it more or less approximates a differential output. And what is the DC voltage here? So let's assume both these NMOSs have a DC VGS of VGSQ given by VOV plus VTN. So what will be the DC voltage at the output? Common mode outputs. Common mode voltage at the output, VOCM. Can I say it is VDD, the voltage at this point, minus VGS. So minus VGS, so which is VDD minus VOV minus VTN. That's the overall voltage here. So that's it. We have just introduced how to, we have discussed how to convert a single-ended signal to a differential signal. So this is the circuit which we will need. We'll have to take a single-ended signal with some common mode, with some DC voltage and generate two differential signals, and both these differential signals should have same DC common modes. That's the most important thing. They both should have same DC common modes. And any supply perturbation should be seen equally by both the nodes. If there is some supply variations, both of them should appear equally on both the nodes. So then we have designed a differential signal. The next part of this differential is how to convert differential to single-ended. I need to build a circuit which can actually take a differential input as two differential inputs, okay, and they can have common mode noise as well. They can have some unwanted common mode noise attached to them, okay, and I'm supposed to ignore that and only generate an output, a single-ended output. I'm supposed to generate a single-ended output which will respond only differentially. So meaning it should be A times the differential input, Vi plus minus Vi minus. And for common mode, it should offer 0 voltage gain. So it should not respond to any common mode changes. So we need to build a differential to single input amplifier which can do this for us. So one of you are asking me what is the DC voltage at this point. So to know the DC voltage here, you should know the DC voltage at the gate. So if DC voltage here is VG, let me call it VICM is the DC voltage, then the DC voltage at Vx is going to be VICM minus VGSQ, VGSQ being VGS of this transistor. It will be VCM minus VGSQ. AC level will be VI2, yes, exactly. AC level will be VI by 2. See, I'll just give you guys another simple circuit. So for example, if you take a circuit like this, apply VI here, you can show it yourself. This will be at minus VI by 2, this will be at plus VI by 2. Okay, both of them. So this circuit, oftentimes we also call it as phase splitter. Okay, it can take one single phase sine wave and generate two sine waves of opposite polarity. Okay, it can split the phase into two. So you get two different sine waves with half the amplitudes. Okay, so on the lower side, you can see it's like a common drain amplifier with 1 by GM load. On the drain end, it's going to look like a common source amplifier with source degeneration. So you will get a voltage of minus VI by 2. The problem here is that the DC common mode is different anyways. The DC common mode is different for both. Do you see any other problem with this? Can I use this as a purely differential output? Do you see any problem with this? Do you see what is the problem is, if there is any perturbation on the supply, yeah, DC level is different. On top of that, if there is any perturbation on the supply, it will directly reach this point. But for the supply, to this point the transfer functions will be different. So yeah, even though they are differential in nature, small signal wise, the supply transfer functions are different. So may not be a very good single to differential converter. Okay, so one of you're asking this, what is the DC voltage? Upper MOSFET DC, yeah, of course, the DC level is very different. The DC here and the DC here are very different. I mean, this DC is determined by whatever input common mode you apply DC minus the VGS. The output upper MOSFET's DC is very different. Okay, but the DC between these two these two nodes, the DC voltages are same. So yeah, that's it. So let me come back to this discussion. I'll just take 2 minutes and then we'll finish the discussion. So we need to design an amplifier which should be able to amplify the differential voltage between two nodes, and it should not respond to any common mode variations. So that is what a D2S does, a differential to single ended amplifier does. One of the simplest ways that I can realize a D2S is this. Can I simply take a differential pair which is going to carry a resistive load differential pair and just take this output as a single ended output? Can I do that? So I've applied VI plus, VI minus to the differential pair, and can I just directly take the drain voltage of this MOSFET here as output? See, what will be the output here? What will be the value of V0 here? Let's assume this node will anyways, if you apply differential signals, this node will come to AC ground. So what will be your output voltage V0? First, let's apply superposition. Let's assume there is no common mode signal present. So can you tell it to me in terms of VI? So it will be VI by 2 and this is minus VI by 2. So what will be the voltage at this point? Small signal voltage. So this node is at AC ground plus GMR times VI by 2, right? That's the small signal gain at this point. That will be yours, because input is minus VI by 2, you will get a positive output, so it will be plus. Okay, So this is fine. I mean, so why can't I just use this as a differential to single-ended converter? I mean, this output is a single-ended output. I'm getting an output which is proportional to this. Can I use this as a single-ended output? Is there a problem with this? If I apply a common mode input, VCM, what will any common mode appear at this output? Will a common mode appear at the output? Yes, right. So let's assume this node, this tail transistor has an output resistance of ROT. Can you tell me approximately, if I apply VCM on this node, what will be the response due to VCM at the output node? What will be the response at the output node due to the common mode inputs here? Right, see, we have already analyzed this. It will be GM times 1 by 2 GM ROT. 1 by 2 GM ROT. It will be GM by 1 plus 2 GM ROT times R into VCM with a minus sign. This will appear at the output. Okay, the 2 is important here. So it will be GM by 1 plus 2 GM ROT times R. That component will still appear at output. So therefore, it's not fully differential. A fully differential to single-ended converter, I mean, that should reject common mode variations at the input. It should not respond to, if you apply any common mode at the input, the amplifier should ideally not respond to that. It should generate an output voltage which is some gain times the differential input. So therefore, it should have no common mode component. It should give you zero gain for the common mode component. So therefore, I cannot use this circuit directly as a differential to single-ended converter. So we have to do some modifications which we will discuss in the next lecture.